In this video, we're going to take a look at practice quiz number 7 on regression. Number 1 says the table below lists temperatures measured in Fahrenheit and Celsius. Find the linear and quadratic regression equations and correlation coefficients. State which model, linear or quadratic, best fits the data. Determine the equivalent temperature in Celsius degrees for a body temperature of 98.6 degrees Fahrenheit. So I'm going to start by adding the table into Desmos. So I'll push the plus sign. And I just want to add these numbers like they look in my table. So degrees Fahrenheit are my X values. So you just want to always be careful not to miss any numbers, of course. So then I want to type 0, 20, 30, 50, 70, 90, and 100. So I get my equation typed in, and it wants the linear and the quadratic equation, so I need to write down both. So I'm going to put y sub 1 is approximately mx sub 1 plus b. So that'll be the linear one. So let's write that out. So I'm going to put linear is y equals 0.56, I'm just going to round to the nearest hundredth, x minus 17.78. And then the r square value equals 1 for linear. So then let's look at quadratic next. So for quadratic, I'm just going to go in another row and put y sub 1 is approximately ax sub 1 squared plus bx sub 1 plus c. And write that one out. So that will give me y equals, and then a is 0. So I'm just going to write it as it looks for a minute. So 0x squared, b is 0.56, and c is negative 17.78. And then the r square value equals 1. So if you notice, 0x squared really is just 0. And then what this turns into is the quadratic function looks just like the linear function. So the best fit would be the linear function. And we can probably zoom out a little bit to look at it and see that like the linear, let me turn off the quadratic for a minute. The linear equation does fit really well through the points. The r square value is 1. And then the quadratic function really is the linear function because of the 0x squared that cancels out. So then the last thing we need to do is figure out the equivalent temperature in Celsius. So that's asking us to find the y value when x equals 98.6 degrees. So what we can do, I'm just going to take out the quadratic equation now. So I'm going to type x equals 98.6 and then just find where that crosses my line, which was 37. So it's 37 degrees Celsius goes with the 98.6 degrees Fahrenheit. So that's it for number 1. Let's look at number 2. The accompanying table shows the amount of water vapor Y that will saturate 1 cubic meter of air at different temperatures X. Write an exponential regression equation for this data set. So we know we need exponential. Rounding all values to the nearest thousandth, so that's 3 places after the decimal. Then using this equation, predict the amount of water vapor that will saturate 1 cubic meter of air at a temperature of 50 degrees Celsius, and round your answer to the nearest tenth of a gram. Okay, so let's get started. Let me clear out Desmos and add in this table. So I'm going to put negative 20, negative 10, 0, 10, 20, 30, 40. And then I'm going to put 1, 2, 5, 9, 17, 29, and 50. And then I'm going to find my exponential equation. So y sub 1 is approximately a b to the power of x sub 1. and then I get my exponential regression equation. So that would be, oh, let me get my pen. Y equals, and then the A is 5.26, or it says round to the nearest thousandth. So 5.265. B would be 1.058, because thousandth means 3 places after the decimal. And then I need to put my X for my exponent. And then it says, using this equation, predict the amount of water. So the amount of water is the Y value that will saturate 1 cubic meter of air at a temperature of 50 degrees. So they're asking you to plug in X equals 50 and find the Y again, like the last question was asking. And they typically ask that, not always, but a lot of times. So if X equals 50, I just need to find where those touch. My prediction equation is in blue, and my Y equals 50 is in red, and they touch at Y equals, which will be the water vapor in grams. So that's 88.4, because they said round to the nearest tenth of a gram. And so then that would be it for that question. All right, number 3 says the table gives the amount of daylight in hours and minutes in Sydney, Australia on the first day of every month. Write out the sine regression equation. For what period of time during a year does Sydney get a minimum of 12 hours of daylight? All right, so I'm going to clear it all out again and type in my table. So for the months, I'm just going to put 1 through 12 in my X values. And then for the time, I'm just going to turn those into a decimal. So 14.22, 13.44, because it's like military time, so it works as a decimal for now. Then I had 11.44, 10.45, 10.03, 9.56, 10.27, 11.23, 12.25, 13.27, and 14.13. So I get all my data typed in, and it said the table gives the amount of hours in daylight. So it doesn't, oh no, it does say the sine regression. I thought it said that. So I need to find the sine regression equation that goes with my table. So y sub 1 is approximately a sine, and then parentheses, b x sub 1 plus c, and then outside the parentheses, you want to put plus d. And we want to write that down because they asked us to find the equation. So y equals, a is, and I don't think they asked us to round it to a certain amount, so I'm going to round to the nearest tenth. So a is 2.3, and then I don't need x yet. I need sine. B is 0.49, so let's say 0.5 x, and then C is 1.5, and D is 12.1. So if I use this equation, it says, for what period of time during a year does Sydney get a minimum of 12 hours of daylight? And so what I'm going to do is change my window to match my data. So I have like 1 through 12. I'm going to put 0 to 13 for my X values because that's just a little more outside of the 1 through 12. So like, let me write that down. So X is between 1 and 12, but then I just use 0 and 13 to be a little outside of that. And then the smallest amount of time was, let's see, looks like 9.56. So I'm just going to put 9 to the largest amount of time was like 14. So I'm going to put 15 and just take a look at what I got. So I got my nice looking sine equation with my prediction equation going through all the dots really nicely. For what period of time during a year does Sydney get a minimum of 12 hours of daylight? So 12 is the Y value. So I'm going to type Y equals 12 and take a look at what I can see. So Y equals 12. So notice from, like, it dips below 12 at 3.45, to 9.78. So it said a minimum of 12, so that would be things that are above the 12. So from January to like the middle of March, it looks like, because that's the 3.5-ish. So like y equals 3.5, and then it comes back up to 12 at 9.8, which is around like September. So I would say, for what period of time? So from January, and let's see, for this one, yeah, let's say January through mid-March, it has a minimum of 12 hours of daylight. And then from the middle of September, it looks like 9.8. So like that's kind of late September. Let's put late September through the rest of the year, which would be like December. So it's really late September through the middle of March, because that's where they connect. So let me write that a little better, because like the year would continuously keep going. So I've decided to write it a little differently. So this late September, but then December would carry over into January. So we would say late September through the middle of March, approximately, because y was equal to 3.5, and then it dipped below 12 and came back up around 9.8, like we can see on the graph. Okay, so let's look at number 4. Which type of function, linear, quadratic, or exponential, would best fit this data? All right, so let's type in the data again, and we'll check it out. So I got 0, 1, 2, 3, 4, and then 1, 2, 4, 8, and 16. And so I want to check out all my options, so I'm going to type each one in. So y sub 1 is approximately mx sub 1 plus b. And I'm going to write that out. So linear would be y equals, and I have the m is 3.6, and then x minus 1, and then the r square value equals 0.871. Now let's do quadratic. I'm just going to leave linear right there and look at quadratic. So y sub 1 is approximately ax sub 1 squared plus bx sub 1 plus c. Okay, so let's write down quadratic is y equals a, which is like 1.14x squared, minus b, because it's a negative, so 0.97x, plus c, which is 1.29, and then the r square value for this one is 0.994. So that's really strong. That's stronger than linear so far. And then let's find exponential for the last one. So I'm just going to go in another row and put y sub 1 is approximately a b to the power of x sub 1, and write that down. So that would be y equals a, which is 1, b, which is 2, and the power of x, and then the r square value is equal to 1. So in this case, that is the strongest model because the r square value is equal to 1. And then we can also look and see our points on the graph. And so if we turn them off individually, and let me change the color of exponential real quick so we can look at them separately. So if I turn them all off for just a minute, and I see my scatter plot, and I turn on the linear one, and I take a look, it looks okay. And then I look at quadratic, it's all right. But the exponential one is definitely like visually the best fit, and the r square value equals 1. So these are all good reasons you could list out. So I would write down exponential is the best fit because definitely r squared equals 1, and the prediction equation fits through the scatter plot, let's say, best. Like, definitely connected most of those dots better than the other options. What is the correlation coefficient for this function? So we already found that. That's the r squared equals 1. And then use the regression equation to predict the value of y when x equals 7. So you can just plug that in and say y is going to be 1 times 2 to the power of 7. And you can also just type in x equals 7, like we've done a few times already, and find it, let's see, up here at 128. So whether you just plug it into your calculator or you put it in Desmos, you get y equals 128. So that's it for number 4. One more to go. So number 5 says the data given below shows the height at various ages for a group of children. Given the best fit line as y equals 0.634x plus 64.945, we want to find the predicted values, the residual values, and answer the question, is there a pattern, and is this a good model? All right, so let's take a look. First, I'm going to clear everything out and type in my data again. So, let's see. We have 18, 19, and then I think it just goes up by 1 until I get to 29. All right, so then I'm going to type in the y values. All right, I got that. And then I know it's linear, so I'm going to type in y sub 1 is approximately mx sub 1 plus b, and get the linear equation, which should just match what they've already got over here. And it does. So then I can find my predicted values. So I'm going to type in that equation now. So I am just going to type exactly what they gave me over here. So y equals 0.634x plus 64.945, and then pull up a table of values in that box. And it just gives you a standard amount it's starting with. So I'm going to need to type in the x values that I need. So I'm just going to take these out. So I need 18. And that would give me 76.4. Then I need 19. So that's 76.991. I'm just going to write that down. And then I need 20. Let's see, I need 21, 22. I'm just going to write them all down. Okay, so 20 is 77.63. 21 is 78.26. 22 is 78.89. 23 is 79.53. 24 is 80.16. 25 is 80. We'll just say 80. 26 was 81.43. 27 is 82.06. 28 is 82. Let's say 7. And 29 is 83.3. Okay, the only other thing I need now is the residual value. So I go back up here to where I typed in my linear model and hit plot. and then they show up in the table right next to the values that I had already typed in. And so I just need to write those down carefully. So negative 0.355, which should be the difference between the actual minus the predicted, is what's going to give you that number. So notice like 76 is a little bigger than 76.4, or a little smaller, so it turned out to be a negative. All right, so the next one is 0.11, and if I did 77.1 minus the 76.991, I should get approximately my residual value. And then 78.1, so I'm just going to write all these down. So 0.477, 0.043, negative 0.09, negative 0.12, negative 0.26, negative, or 0.51, let's see, negative 0.33, negative 0.06, negative 0.09, and then 0.17 are my residual values. So then I need to answer some other questions. They have already plotted the residuals over here, so I don't have to plot them. I notice there's no pattern to that residual plot, which is a good thing. I also noticed the R-square value over here is 0.9852, which is another indication that this is a good model. So is there a pattern? No. And that's referring to this residual plot, how there's no pattern. It doesn't look linear, quadratic, exponential at all. There's an equal, or let's see. We have 1, 2, 3, 4, 5, 6, 7 data points below the x-axis. And then we had 1, 2, 3, 4, 5 above the x-axis. So it's pretty well scattered around the x-axis. So we would say, no, there is no pattern. And then, yes, this is a good model. All right, so that is it for practice quiz number 7 on regression.